is go ahead and turn to page 18 in your course pack. And we're going to talk about ways that heat is transferred from one object to another. There are three main ways that heat can get transferred. And you guys have actually learned all of these before in 6th grade. So help us out, and which ones do you remember? Ways that heat is transferred. Convection is one of the ways. What's another way that heat can be transferred? Conduction. And the last one? Radiation. Convection, conduction, and radiation are the three ways that heat can be transferred. And so right here in front of us, we're looking at all three examples, and I want to show you how they work. So the first thing let's do is, just because it takes a little while, is we're going to get started with conduction. Conduction is when heat is transferred directly from one substance to another by touching. Remember, heat is the transfer of thermal energy. So conduction is when something directly touches something else and it takes the heat from one thing and goes to the other. That's conduction. Heat will always move from something that is warmer to something that is colder. Always. It always goes from hotter to colder. Okay? So if I take a soda can and I put it in a cup of ice, alright, I take a soda can, a warm soda can, and I put it in a cup of ice, the can of soda does not steal cold from the ice cubes. In fact, the ice cubes steal heat from the soda can, which lowers the temperature of the soda can and simultaneously melts the ice. Alright? That's how that works. So to show you conduction, and that different substances conduct heat differently, here I have 3 Nestle Crunch bars stuck on the ends of 3 different types of metal rods. I have a copper rod, an aluminum rod, and a steel rod. Okay? So we've got all 3 rods, and what I'm going to do is I am going to pour boiling water into this small thing down here.
Which will melt first.
Okay, and we're going to be able to see how different metals react and conduct the heat based on whichever one of these chocolates melts off the stick first. Okay? Well, it's leftover Halloween candy. You probably don't want to eat it. I know. You'll all eat all the sorts of junk food. Okay, so we're just going to let this sit here. But while we're letting it sit here, I want to talk to you a little bit about something called specific heat capacity. Okay? Specific heat capacity is directly related to conduction. Because specific heat capacity is how good something is at keeping its own temperature. Alright? So, how good is metal at keeping its own temperature? I would say that it's actually pretty bad at keeping its own temperature. Think about it. If you had a metal bench outside, in the winter when you sit on the metal bench, how does it feel? Okay? If you sit on the bench in the summer, how does it feel? Is the metal good at keeping its own temperature? No. Now compare that to something like wood. If you have a wood bench in the winter, is it always freezing cold?
No.
What about in the summer? Is it always boiling hot? No. Okay, so different substances can have different what are called specific heat capacities. How good something is at keeping its temperature is its specific heat capacity. And so if something is very, very good at keeping its own temperature, we call that a high specific heat capacity. So wood has a higher specific heat capacity than something like metal, which has a very low specific heat capacity. Does that make sense to everybody?
Does that relate to how well it conducts heat?
How well it conducts heat is related to its specific heat capacity. So the higher the specific heat capacity, the not as good a conductor it will be of heat. Okay? Remember, to be a good conductor of heat, that means it's going to easily pass that heat along by touching something else. Okay? So we're just going to sit here and let these different rods drop. But my question for you is, which rod, okay, will the chocolate melt the fastest on? The one with the highest specific heat capacity or the one with the lowest specific heat capacity? Lowest. Lowest. Definitely with the lowest. All right? And which one do you think it will be? We have steel, aluminum, and copper. Which one is going to have, do we think, the lowest specific heat capacity?
Aluminum. Copper.
Copper. I'm hearing all of them. Okay, well, we'll find out in just a few minutes when this chocolate decides to, get on its way. But for now, I'm just going to push it off to the side. If anyone notices it, sliding down the post, just let me know, and we'll take a look and see which post fell first.
Sliding them.
All right, over here, we have boiling water. Right? This does not seem too exciting. But this is actually a perfect example of all three types of ways that heat energy can be transferred. First of all, we have conduction. All right, we have the hot plate, which is quite warm because of the electricity that's running through it, and it's touching the glass, which is touching the water, which is making the water hot, which is making the water boil. All of that is conduction. All right? We have radiation. I can put my hands without touching them and feel that the hot plate is hot. Okay? When something radiates, that's the transfer of heat through space. Okay? It does not necessarily have to go through a medium. So thermal energy can be transferred through space. Can anyone think of the biggest example that we have of that?
The sun.
The sun. All right? Our sun sends us a lot of thermal energy, and that heat warms our planet. Okay? And so that heat is radiation, and it's coming off the sun. So you don't necessarily have to be able to see it to feel it when it comes to thermal radiation. Okay? So while light is often involved in radiation, it doesn't have to be there for radiation to exist. Is everybody on board with that? Okay. So then the last thing I want to show you here is convection. Now, convection is the transfer of heat in a circular motion through a fluid. A fluid. Now, I'm specifically saying fluid here and not liquid, because in science, the word fluid means a liquid or a gas. A liquid or a gas. So there's like a college class you can take in engineering called the engineering of fluids, and that's how things move in the air or things move in the water. Okay? So, to show you convection, I'm going to take some macaroni noodles and chuck them in this water, which is rapidly boiling. Okay? And we're going to watch the motion of the noodles. Alright? That's the job for right now. This does not seem like an exciting job, and it's not really. Okay, we're going to push them a little towards the middle so that they work a little bit better. Okay? Now, what we should see in not too long a time, as soon as the noodles start to get warm, is that the noodles are going to rise to the top. They're going to cool down once they get up here because they're going to come in contact with the air, which is cooler than the water. And then as they cool, they're going to drop down because heat rises, right? We know that heat rises. And so the noodles are going to start to come up, and they're going to start to make a loop, all right? You probably noticed that when you make pasta at home, okay, when you make pasta at home, do you just put it in once the water gets hot and starts steaming? No, you wait until it's at a rolling boil. And one really fun fact is that if you're making noodles at home, you actually don't have to sit there and stir for the entire time the noodles are in the pot.
What?
I know, magic trick. If you wait until the water is rapidly boiling, and all you do is stir until the water boils again, then once you take your stirring mechanism out of the water, it will stir itself using convection.
Whoa.
Your noodles, as long as you put enough water in, will not get stuck together as long as you stir it until it comes back to a rapid boil. Because if you ever have a rapid boil, you put a lot of noodles in, what happens? It stops bubbling, right? Yeah, you're going to see some of them are starting to rise. It takes a little while because they got to get warm, but they're going to come up and drop down, come up and drop down. So we'll give that a few more minutes to get itself working. How are we doing on this one? Good? Does everybody understand convection? Yes. Convection also works in the air. So you can't really see the smoke clouds here, but if you were at a bonfire or something, you would see that smoke would come up, and it always makes a nice little circle. Because hot air rises, but then as it reaches the cooler air above it, it will cool and settle back down again. And it will always work in a nice little circle. Okay? And that's called a convection current. A convection current. Are there any questions about conduction, convection, and radiation? Those are the 3 ways heat is transferred. All right, so right now, if you could please, on page 18 in your course pack, I want you to write down your own example, maybe add to the examples that you can think of conduction, convection, and radiation. All right, thanks, Corinne.